A few brief thoughts then on the uses of radioisotopes, beginning with a nice graphic on radioactive decay. You should know that decay is both random and unpredictable, and you should know what we mean by random and unpredictable. Unpredictable, you don't know when it's going to happen. Random, you don't know how many will decay in the next given period of time. Neither do you have any control over it. You can't speed it up, you can't slow it down, you can't change it, you can't stop it. It just happens. So this graphic is showing you the random nature of the decay. And of course, when you have lots of parent nuclei decaying into stable daughter nuclei, initially the activity, the number of decays per second, is going to be higher than later on when there are fewer nuclei left to decay. And so you can see here that the number of blue spheres turning red every second is less. Uses then. As I've said before, uses are largely gamma sources. Most of the things that we do with radioisotopes involve gamma sources. Not all of them, and you'll see one use here that doesn't, but here medically we use gamma. Here we have an external gamma source, that is to say it's not inside the body, and it's being rotated around the body in a circle, and the tumour, the cancer that we're aiming the gamma rays at to kill it, the tumour is in the centre of that circle. So wherever the source is, it is firing gamma radiation at the tumour. However, the healthy tissue all around the tumour is getting a much lower dose, so it is safer. The other thing about it is that cancer cells are more susceptible to damage by ionizing radiation than normal healthy tissue on the whole. Because cancer cells are rapidly dividing cells, they are more susceptible to damage than cells which aren't rapidly dividing. Of course, the body does contain rapidly dividing cells, sperm cells, and hair cells are rapidly dividing, and so these are susceptible to ionizing radiation too. They're also used, gamma radiation is also used to sterilize equipment. So you can, when you're manufacturing syringes, for example, for medical use, you can manufacture them, package them up in airtight containers, and then you can irradiate the whole thing with gamma radiation to kill the bacteria on it. And it is sterile then. Here you have an example of tools being irradiated to sterilize them. Strawberries too, for example, soft fruits are irradiated so that they last longer on the shelf because the bacteria have been killed. That doesn't mean they're contaminated, it doesn't mean that there is radioactive material on them. Gamma rays have passed through them and killed the bacteria. The strawberries themselves are not contaminated, neither is this patient contaminated, neither were the utensils, the surgical instruments, they were not contaminated. Gamma rays had passed through them and killed the bacteria on them and in them. And here gamma rays are passing through this gentleman, and the gamma rays are being absorbed principally by the cancer cells and killing them. Another use is the automatic thickness control for paper mills, for aluminium foil manufacture, making sheets of anything really. And so we have a beta source here, we have a detector here, and the detector sends a signal to the control system to control the distance between the rollers. So you can automatically set the thickness that you want, and the rollers will be controlled to maintain that thickness, so that you are making a uniform product. When we buy paper, we want the paper to be the same thickness across the entire surface of the paper. And the manufacturer doesn't want to put more material into that than we're paying for. So there's two reasons why you want your paper or your aluminium foil or whatever to be uniform thickness. Now you can't use alpha because of course the alpha would be absorbed by the paper. You can't use gamma because it would be unaffected by the paper or the aluminium. And so beta is the thing to use there. So while I said virtually every use is gamma, here's an example of a use of beta. And a smoke detector would be an example of the use of alpha. Now, you can also use radioactive sources to check leaks. If you had a pipe and you knew that you had water leaking out of your pipe, you didn't know where, if you put a little bit of gamma source into your water, as the water travels down here, when it gets to the leak, the gamma will come out with the water. And so as you move your detector across the surface, maybe the road, you'll detect a constant reading where there is no break in the pipe, but here the gamma will be building up and you'll get a bigger reading, so you'll know where your leak is. And the same thing, of course, whatever the liquid being carried or even the gas being carried in the pipe would be. Tracers in medicine, again, gamma source, where you inject the radioisotope into the body and you can follow its path around the body using a gamma camera. You can check for overactive or underactive thyroid glands. You can check for the uptake in the tumor, so you can find the tumor in the lungs or the brain. And it has a short half-life of hours so that the healthy cells are not overexposed, but you get a constant reading during the procedure so that you can make your measurements and make your conclusions based on them. Radioactive dating, well, there are two principal uses for this: dating rocks, very old things, and dating once living things using carbon dating. So dating rocks, you have uranium-238 in the rocks, and it decays ultimately to a stable isotope of lead. Well, that takes about 4.5 billion years for the half-life. So you can tell from knowing the concentration of uranium-238 that you would expect and knowing the concentration of lead that you have, you can work out how long it's been since that rock was formed. And there you go. So as the concentration of lead rises and the concentration of uranium falls, you can work out the age of the rock. Carbon dating. Living things exchange carbon-14, which is a radioisotope of carbon, with the atmosphere while they are alive. When they die, they stop exchanging carbon-14, and so the proportion of carbon-14 in the organism's carcass falls. And so knowing how much carbon-14 you expect and knowing how much carbon-14 you've got, you can work out how old your item is. But it only works for once living things. And you can see here, if the original activity was 16 becquerels per gram of wood, and it's now down to 12, that is 75% of what it was before. You can read off the graph and you can say, well, that's 2,400 years.